Okay, so the next speaker will be Lia GANDER from the Center for Computational Medicine in Cardiology at the Università della Svizzera italiana in Lugano, Switzerland. And her talk will be about fast characterization of inducible regions of atrial fibrillation models with multi-fidelity Gaussian process. So please, Lia.
Thank you for the introduction. So this is a joint work together with Simone Pezzuto, Ali Garaviri, Rolf Krause, Paris Perdicaris, and Francisco Sali Costabal. I start with motivation. Atrial fibrillation is an arrhythmia characterized by the chaotic beating of the atria caused by the self-sustained propagation of the electric potential on the atrial surface. Some regions of the atria are more likely to induce atrial fibrillation than others. The inducibility is affected by the atrial geometry and the remodeling, for example, in the form of fibrosis or ionic channels changes. It can also be affected by some treatments, like antiarrhythmic drugs or ablation, that have the purpose of reducing the inducibility. For these reasons, it is important to be able to determine the inducibility of various models. And this motivates the interest on the fast characterization of the inducible regions of atrial fibrillation models. Now I present our computational model. We have this realistic 3D geometry of the atria with 70% fibrosis that is given here in yellow. Note that the fibrosis was not applied on the Bachmann's bundle here and on some regions with isotropic conductivity. On this geometry, we solve this monodomain equation for the evolution in time of the transmembrane potential Vm. The other terms in this equation are the membrane capacitance Cm, the surface to volume ratio beta, and the monodomain conductivity tensor Gm. Then we also have the transmembrane ionic current density I-ion, that is a function of Vm and of the state vector Y. The state vector is described by the function capital F of the ionic model, that in our case is the Kurtmonsch-Ramirez-Natter model from 1998. And finally, we also have the stimulation current density IS. To complete our model, we need to be able to evaluate the atrial fibrillation inducibility. For that, we consider a pacing protocol consisting of 15 stimuli delivered at this time instance with decreasing intervals between delivery times. Depending on the pacing site, the protocol might induce atrial fibrillation or not. So our goal is to determine the regions that induce atrial fibrillation. In other words, we want to derive an inducibility map of the atria. This is a classification problem in which we want to assign class probabilities between 0 and 1, where 0 means that atrial fibrillation is not inducible, and 1 means that atrial fibrillation is inducible. Before presenting the solution methods, I show here two examples of simulations with different pacing sites, one inducing atrial fibrillation and one not inducing. So the first one is the one inducing. We have the pacing site here, and now we see the pacing protocol. Now the pacing protocol is over, and we see that the potential keeps propagating in a self-sustained way. And the potential will keep propagating this way until the end of this simulation. And this is the example not inducing. Now the pacing site is here. And again, we see the pacing protocol. Now the pacing protocol is over, and we have seen that the wave simply vanished. And now there is no more activity until the end of the simulation. Okay, now we go back to our classification problem that we want to solve using multi-fidelity Gaussian process classification. Before going into that, I recall the main principles of single-fidelity Gaussian process classification. So we start with a data set of input-output pairs, xi, yi, where xi are some pacing sites and yi are the corresponding classification outputs, so either 0 or 1. Then for any location x on the atria, we want to assign a class probability sigma of f of x, where sigma is this function here with range in the interval 0, 1, and f is called the latent function. Such f is assumed to be a Gaussian process with zero mean and the covariance kernel k that depends on a set of parameters theta. And a prior distribution is assigned to theta. Then the procedure is the following. We first compute the posterior distribution over theta based on the dataset. Then for a new location x star, we sample f star of x star from a normal distribution with the mean mu of x star and variance sigma of x star, where this mu and sigma arise from conditioning on the available data that are denoted here with capital X and have this form. And then finally, we compute sigma of f star of x star for all realizations, and we take the mean to obtain the prediction y star. In the multi-fidelity case, we have two models with different levels of fidelity. A low fidelity one denoted with capital L, and a high fidelity one that we denote with capital H. As a consequence, the data set is now composed of both low and high fidelity data. And another consequence is that we now have two latent functions, FL and FH. Their structure is assumed to be the following. FL is a Gaussian process with zero mean and covariance kernel KL that depends on the parameters theta L. And FH is equal to rho times FL plus delta, where rho is a parameter to be inferred, and delta is a Gaussian process independent of FL with mean 0 and the covariance kernel KH that depends on the parameters theta H. Because of this structure, the function f that is now defined as a vector with components FL and FH is a Gaussian process with zero mean and matrix valued covariance kernel with these entries here. And another consequence is that now we have to assign prior distributions to all theta L, theta H, and rho. The rest of the procedure is the same as in the single fidelity case, but with another dataset, another function f, and other parameters. So as we've seen, Gaussian process classification requires the computation of some kernels. This is not straightforward in the case of Gaussian processes on surfaces. So I present here the technique proposed in this paper about Gaussian processes on manifolds. So we consider a manifold M that in our case is the atrial surface with topological dimension d equal to 2. And we consider the Laplace-Beltrami operator delta. The negative Laplacian admits this representation where lambda n are the non-negative eigenvalues and phi n are the corresponding eigenfunctions. Then the kernels of the Matern family with the smoothness parameter nu are given on M by this formula, where the set of parameters theta is composed of eta and L. And in practice, this sum is truncated, and this allows us to compute the kernels on M. Now I present our multi-fidelity models. So we performed the simulations using a second-order finite difference method on a mesh with space resolution H. And we integrated the monodomain equation with an explicit implicit method with time step delta t. For the high fidelity model, we consider a fine mesh with resolution H equal to 0.2 millimeters and the time step delta t equal to 0.01 milliseconds. For the low fidelity model, we considered a coarser mesh with resolution H equal to 0.4 millimeters and the time step delta t equal to 0.02 milliseconds. The simulations were performed using the ProPag5 software on CSCS, the Swiss National Supercomputing Center. And so for 4 seconds simulations, the computational time of the high fidelity model is 1 hour and 40 minutes with 8 nodes, whereas the computational time of the low fidelity model is 14 minutes with 4 nodes. So the low fidelity model is approximately 16 times faster than the high fidelity one. So the idea is to exploit the information provided by the low fidelity model to speed up the computations. I conclude with this slide with a remark. Since the coarser space discretization has the effect of reducing the conduction velocity, we have to adapt the surface to volume ratio beta in the low fidelity model. So for the high fidelity model, we have beta equal to 800 centimeters to the minus 1. And for the low fidelity model, we take beta equal to 450 centimeters to the minus 1. Before presenting the Gaussian process classification results, I show here the ground truth that we will use later to compare the accuracy of the single fidelity and the multi-fidelity classifiers. So these are the outputs of 100 high fidelity ground truth points. The red points are those that induced atrial fibrillation, and the blue points are those that didn't induce atrial fibrillation. And these are the Gaussian process classification results. These results were obtained using training points that are different from the ground truth points that I showed in the previous slide. So here we have, this is the single fidelity classifier trained with 50 high fidelity points. And this is the multi-fidelity classifier trained with 50 high fidelity points and 100 low fidelity points. The balanced accuracy compared to the ground truth of the multi-fidelity classifier is 85% against the 78% of the single fidelity classifier. The better performance of the multi-fidelity classifier compared to the single fidelity one is also confirmed by this plot, where on the x-axis we have the cost, and on the y-axis we have the balanced accuracy of the corresponding classifier. The blue line refers to multi-fidelity, and the red line refers to single fidelity. The number of high fidelity training points ranged from 20 to 100 for both the single fidelity and the multi-fidelity classifiers. But in addition, the multi-fidelity classifier also exploits 100 low-fidelity training points. And this is why the blue line of multi-fidelity is shifted to the right by the cost of the 100 low-fidelity samples. In general, we can see that with equivalent cost, the multi-fidelity accuracy is higher than the single-fidelity accuracy. So from this, we can conclude that the multi-fidelity classifier performs better than the single-fidelity one. I conclude the presentation with an outlook on a possible future improvement. This is active learning, and the idea is to estimate the next point, x new, to sample the model so that the accuracy of the classifier increases the most. So out of a set of candidates, the point x new is the one that minimizes the ratio between the absolute value of the posterior mean and the square root of the posterior variance. The reason for this optimization problem is that we want to balance two concepts. On the one hand, we want points that are close to the classification boundary, where sigma of f of x is approximately 0.5, which means that f of x is approximately 0 because of our choice of sigma, and the posterior mean is small. On the other hand, we want points that are far from the training data, so where the posterior variance is large. So after getting the point x new, one can then compute the corresponding classification label y new by evaluating the model. Then we add the new input-output pair to the dataset, and we retrain the classifier. So this discussion on active learning concludes my presentation. Thank you very much for your attention.
Okay, thank you very much for your presentation. We have time for a couple of one or two quick questions. If there's any from the audience.
Hi, Pasquale. I would like to ask a question if possible.
Yeah, sure. Please go, Luca.
Hi, Lia. Hi, thank you so much for the presentation. That was a really nice one. I actually have a question about your inducibility protocol. So the first question is, are you using different, are you using heterogeneity in the ionic model in different regions of the atria, or maybe I missed that, or are you using always the same ionic model in all the regions of the atria? So do you think that the inducibility could be, I mean, I proved in my latest paper, you can check it out, that the inducibility is depending on the pacing protocol that you're using, on the inducibility protocol that you're using. So do you think that trying different protocols would actually give you a different result in for your method in deciding which areas are more prone to be inducible or not?
So protocols in the 3D model. So I don't know, but I guess that some results could be different. And since if you say that you tried this, yeah, you're probably more expert than me on that. So I guess that could be a good point, actually.
Okay, yeah, I would be really interested to check if this will make a difference using your classification problem. But yeah, so thank you so much for your presentation, actually. Really nice.
Thank you for the questions.
Okay. Any other question? Okay, if not, I would like to thank Lia again for her presentation.